Okay, so let's do some recap. Okay, so I sent some one problem set which you should try to look at during this course of the school. So one thing you should really, I mean, that's really important and useful to do is just simulate the process, right? And verify some of the results. So for example, this result for a 1D random walk, it's very easy to check on a computer, right? So you can easily write a very short code and verify that if you do a random walk on a lattice, you start from the origin and walk and keep walking till you come back. And let's say it takes n steps, you ask what is the distribution of n. Then yesterday we discussed that this goes as 1 by n to the power 3 by 2. So it's something you should definitely do and verify that this is true. Okay, so so on when you do on the computer, of course, you'll do it usually on a finite lattice, let's say. Okay, supposing you do it on a finite lattice, okay. So supposing you are solving this problem on a ring. So it starts from 0, 1, 2. So there are, let's say there are L sides on a ring, and you are doing this random walk on this ring. Okay? So and you are asking this question. You start from the origin and keep walking, and so you do something, and then eventually come back and ask for the distribution, right? So if you, I mean. So if it's a finite lattice, then of course this result was derived for an infinite lattice, right? So for a finite lattice, this is not going to be true. But if L is large, what you will see is, so if you plot this, let's say P1 n versus n. So initially, of course, it has some form which need not be this. And so this, let's say I'm doing a log plot, right? So log VA versus. Then you'll see this slope into the power minus 3 by 2. But if it's a finite lattice, eventually it gets cut off, right? So it's going to probably, okay, I'm not sure what exactly it will do, but it should eventually decay. Right, okay, so now, so at what time do you expect this to happen? Like at what time? L. So everyone thinks it should be L. At what time, like if I'm on a finite lattice, after what time will I realize that it's finite? It's a random walk. Yeah, so how many people think L square? How many people think L? L square. So most people think L square, yeah. So because random walk typically x square goes as n. So the time to see the full size should be L square, right? So probably we expect that this crossover should happen at L square. And then there'll be some other form. Okay, so now you can ask, for example, one question is like, what is the mean return time, right? So on the infinite lattice, what is the mean return time? So the distribution is this. So if you ask what is the mean time that I will take to return to the origin, so it should be this, right? N. So this is equal to, right? This is the mean return time. So what will this give if we do it on the infinite lattice? Infinite, right? Because it goes up to infinite, so this should divert. So even though we definitely return to the origin, the mean time to return is infinite. Okay. So this is also true in 2 dimensions. You can verify. So I mean, if you are like we discussed this problem, like you start drunk and you walk back, you are walking home. So you'll definitely reach home, but to reach home, it takes an infinite time, right? Okay, so now you can ask on a finite lattice, of course, it should not be infinite, right? It should be some function of the system size. So now what do we expect on a finite lattice? Okay, so what do you expect this? It should depend on L clearly, because L going to infinity, it should be infinite. But what power should this be? So from what we said here, can we try to estimate this N? So, I mean, okay, so one possible estimate would be like, okay, so see here everything is controlled by large N behavior. So the summation we can always convert it to an integral. So we can write it as dn in E1 n, and n now goes from 0 to so after L square it decays much faster. Okay, so there will be some exponential decay. So we can put a cutoff at L square, right? L square. So now if we work this out, so this is dn n, and at large n, this has the form 1 by n to the power 3 by 2. Okay, so this now you can just do scaling, and you'll get what? This goes as, so this is n half, so then it just goes as L, right? Okay, so the mean time to return on a finite lattice is, or so from this argument it's order L, right? Okay, which at first sight it looks a bit surprising, because normally you would have expected that everything scales as L square. So maybe the return time, mean return time should also scale as L square. But it's kind of interesting that it's actually order L. Okay, so now actually there's a very interesting result which is part of the assignment problem, which is that if we, so this we can of course try to like work it out exactly, right? Because we know everything exactly. So if you do the exact calculation, then what you'll find is that, so here of course we made an estimate, but actually for a random walk, this is actually exactly equal to L. Okay. And this result is also true in any dimensions. So if you do it in any arbitrary dimension on a finite lattice, so let's say you have a square lattice with periodic boundary conditions, or it doesn't matter, even with hard walls, whatever. If you find this expected time, then it's exactly, so in d dimensions, like if you have, so let's say the number of sites is n. Okay, so if the number of sites on the lattice is n, then this is always exactly true. Okay, so independent of dimensions, lattice, and you can even put different probabilities for hopping and so on. But this is a exact result. Okay, so this is also part of the uh, assignment problem. So the way to see it, I'll just give one example. Like let's say this 1D lattice. How do you see this result? Okay. So on a 1D lattice, on the infinite lattice, yesterday we showed that. Okay, so we started with this. Basically, we use this relation that f equals to 1 minus 1 by g, right? And then we need the form of g. So on the infinite 1D lattice, g was 1 by 2 pi. No. This is for return to the origin, and then this is the, what is it? We called it the generating function, right? For p. Okay, so now, so first we have to, so this result is always true, whether it's a finite lattice, infinite lattice, and so on. This result, right, the argument we gave to derive this is always valid. Now this will, of course, change on a finite lattice, right? So this, you can try to convince yourself that this will, on a finite ring with sides going from 0, 1 to L minus 1, this is replaced by this formula 1 by L Okay, so basically, instead, like here we did an expansion into e to the power iqx. On the infinite lattice, q is continuous and goes from minus pi to pi. On a finite lattice, q will be quantized, right? And it will take these values, where s goes from, let's say, 0 to minus 1. Okay, so if you take large L, this will go to this, right? This you can try to see. Okay, so now we have to use this result and this formula. Okay, and now so we have f. So f z is basically let's say p1. Okay. So now if you take a derivative and let's say then this is right. Okay, so now if I set z equal to 1, then it's clearly this is the expected return time, right? Because so this np1n, that's the expected return. Okay, so given f, if I do z df dz and set z equal to 1, that gives me the expected return time, right? So now we have f is this. So if you do df dz and so on, then you basically get g prime. And then you have to set z equal to 1. Okay, so g is this. So if you take a derivative, so if you take a derivative, you get basically sum over. Okay, so now if you set z equal to 1, what is this? Z equal to 1, this is infinite, right? Because there is a qs equal to, it goes from all these values. There's s equal, there's a q equal to 0 is there, right? So if you put z equal to 1, at least one of the terms in this summation is infinite. So this will blow up, and similarly, this also blows up. So it's infinite by infinite. So it's so what we have to do is, of course, in fact, not set z equal to 1, but take the limit z going to 1, right? So here now, I won't work out all the details, but basically, you should just separate out the term with s equal to 0 and the terms which are not 0. Okay, so the first term is, sorry, this is the square, right? This is square. Right, yeah. Okay, so you just have to take out the s equal to 0 term. So that will give, let's say, 1 by L. So Z by 1 minus Z square. So this is the divergent term. And then plus there's something. Okay, so let's call it A of Z. And similarly, down here, you have there's a term which is 1 by L square. And then something which we call B of Z. Right. Okay, and then now you have to do some expansion. This is large, and this is when Z goes to 1, this is large, but this is finite, right? So you can do an expansion, and more or less you can see that you will get a L here. Right? So this term is negligible, and I mean, so naively, if you just drop this, you immediately this cancels, and when you set Z equal to 1, you just get L. So it's a kind of very simple proof, but it's quite general. I mean, you can do it for any lattice and so on. It's the argument is the same, but it's quite I mean, quite a beautiful result. That independent of lattice type, everything. I mean, the mean return time is always the number of sites. Okay, any questions? Why multiplying by? Okay, I mean, this was not strictly necessary because otherwise you get n minus 1. I mean, it's not strictly necessary because anyway I'm setting z equal to 1 eventually, but this is, yeah. And also there's a generalization of this formula. If you want n to the power any moment, then it's given by z. So this you can easily verify that this is true. Okay, so so this was just a digression from what? Okay, like yeah. Sorry. The main result. The main result is the mean time to mean return time on a finite lattice of size L, of L sites, is exactly L. In all, so yeah, so L is the number of sites in if you have like a cubic lattice L to the power D or whatever, but number of sites. So I did the proof for one dimensional this on a circle, but you can do it on any lattice and it's true. You can like you can take a box, like finite box with, let's say, reflecting walls, right? And maybe you can put rates P and Q. Okay, so for this case, you can also try to work out. The first return time is completely different, right? In this case, it will be some exponential distribution. But this time will still be the same thing. So this, I mean, you can try to work it out. Okay, actually, I believe this is true, but you should verify that this is true. Okay, any other questions? If it's not clear, I'll just okay. Okay, so now let's kind of continue what we were doing yesterday. So, so yesterday we kind of derived this formula where basically you, I mean, given some generating function Az equals to sum of, let's say, uh, so then we asked like, how do you estimate the asymptotic? So if we know this, given we know this function, how do we find the asymptotic form of an? And we said that basically we need to define this a tilde s equals to a e to the power minus s, and basically look at the function close to z equal to 1. Okay, so which means s going to 0. So okay, and then we basically said that an goes as okay. So for large n, you can we'll use this. Okay. So for 1D random walk, we saw that this basically leads us to Pn. Okay, now let's do the 2D case. Okay, so now first we have to find G. So G 0. Oh, huh? Right by 2. Okay, so now basically we have to again same thing, right? If you put z equal to 1, then we know that this is a divergent integral because this is so right now it's minus pi to pi, but it has if z is 1, then at q1 equal to q2 equal to 0, there's a 1 by this is of the form 1 by q square, and then from here we get q dq. So it's q dq by q square. So that's there's a logarithmic divergence, right, of the integral. Okay, so then we have to basically do the integral very carefully near q equal to at small q, and so we just expand it at around small q, and then we get dq. So here we'll get some q, and divided by 1 minus z, and then plus. So q1 square plus q2 square, which is q square. Okay, now so this so z here. I mean, since we are anyway going to put z close to 1, we can put this as 1, and this integral will give what? So this, of course, we can write as dq square, right? So what will it give? The integral. Yeah, log. So it's log, and then infinity is 0, and at q equal to 0, so this will give, I guess, log of 1 minus z. Okay, everyone agrees, or? Yeah. Okay, so maybe let's do it carefully. Okay, so yeah, so question is, can we set 0 to infinity, for example? Okay, so initially it was 0 to pi. So let's keep it 0 to pi, because otherwise we'll have a problem. So see, basically the upper limit, we don't care what we set it, because all the divergences are coming from small q, right? So let's keep it some finite number. Okay, and then if you do this, we'll get, so this is d of, so du of u by 1 minus z plus u, 0 to some finite quantity. So this is log of uh, 0 to some finite. Okay, so so the upper limit is, okay, so you put something here and you'll get something, but when you put z equal to 1, you'll get a finite number, right? So you don't care. So but the divergence is basically from the lower limit. Okay, so so therefore this is I can set this as log of 1 minus z. Okay, and the sign is what? There's a minus sign. Okay, so okay, so now therefore f1, f is f of z is 1 minus 1 by g, so it will be some constant by, so minus becomes plus by log of z, is log of 1 minus z, and then we set z equal to e to the power minus s, and for small s, this is just log of s. So log of Yes. So for small s is just one, replace z by 1 minus s. Okay, so and then we use this formula. An is the dn of this. So P1n goes as so this is minus and plus, so 1 by. Okay, so this is the final result that we stated yesterday. Okay, so okay, so this is so I think someone pointed out yesterday that so sort of interestingly, this is a bit larger than the 1D formula, right? So in 1D we got, so this is 2D, and in 1D we had 1 by n into n to the power half, right? So this is larger than this. So so if you plot this versus n, so this is, let's say, log n and log p1. So in 1D, so initially there's something, and then it will go like that, and 2D, the probability at large n is kind of slightly higher, right? So it's so which means that this has to cross this curve. Okay, so for small n, the 2D will be lower. Okay, and then it will be a different, slightly smaller slope. Right, so this is 2D. Okay. Yeah, so you can try to think about why this is slightly higher than 1D. Okay, so in both cases, if you ask for the mean return time, then it's infinite. It's on the infinite lattice. So this you can. So this is again. It's very useful if you can if you simulate it and just try to see these power laws and how they look and so on. Okay, so in higher dimensions, I won't do the complete thing, but I'll just state the result. So basically, there, of course, the first observation is that G0, 1 is finite. All right, and so therefore, there's a finite probability that the walk will, so if you do f equal to 1 minus 1 by g, so since this is finite, there's a, so you return with a finite probability, not 1, and so there's some probability that you'll never come back, right? So now you can ask condition that on the fact that I return to the origin, what is the return time distribution? Okay. So you can work this out, and in this case, P1n. Okay, so of course this is conditioned on, you may not return, right? So if you return, then you can show that this goes as 1 by n to the power d by 2. So so if you do this calculation again, what you should find is that f of z is basically R naught. Okay, so this is, so I won't work it out, but I mean, doing like similar kind of calculations, you can show that for z close to 1, it has this kind of a form. Okay, so now we'll do okay, something slightly different. So far we have just been looking at asymptotics, but we can ask, like, can we actually find an exact formula, right, for P of n? So far we only computed at large n what is the form, but can we actually find an exact formula? So for this quantity, let's say P of xn in 1D, this we know the exact formula. So this is n factorial by n. Like, so in particular, if we ask the probability of being at the origin, so we can put 0 here. So then it's just this, right? So this is the probability that after n steps I'm at the origin. So this is some simple. So we want a similar formula for P1n. Okay, so how do we do this? Okay, so basically we'll use this method of generating functions. And so what we need is g of 0z. Okay, so in this case, of course, this is the integral which is can be done easily, right? So how do you do this integral? I mean, how would you do this integral? Contour, right? Yeah. So you can, since minus pi to pi, you can just take a circle and then find the poles and so on. And so this is final. The answer is just 1 by. Okay, so in fact, you can also do it if you put gxz, then also it's easy to do. But let's just focus on return to the origin. Okay, so we'll just do this. Okay, so therefore, so here you can now, if you expand this, so the expansion of this in Z is of course supposed to be P0n Z to the power n. So if you just do a Taylor expansion, you can immediately find P of 0n, and you can verify that you get back this. Right? So, I mean, this we know that if you just expand this, then what we should get is that this is equal to summation. Right. So this is, so if you can expand this, then immediately we can read off this. Okay, but now, of course, we know this is true. Okay, now, so now we find f. So f is 1 minus this, so this is. Okay, so again, we have to, if we do a, if we just Taylor expand this, then we'll get some series which will immediately give us P1 n z to the power n. Okay. So one sort of quick way to figure out this expansion is the following. Okay, so if I take dfdz, then it's you get a z, then half cancels, and so it's basically z. Okay, so this is equal to 7. Yeah. Okay, so dfdz is this. Sorry, this is g of z. Okay, so the reason I'm doing this is because we already know the series for g, right? So then it's good to write it like this. So then we know that df by dz is equal to, since we know the series for g, so we can write this as Okay, so therefore F is okay, just integrate F, so I'll get Z to the power n plus 2 by n plus 1. Okay, so now I can just replace n plus 2 by n and bring it back, rewrite the series, and then immediately I can read off what is the prefactor, right? So this I know I can now just uh, shift n and then compare the two series. Okay. So if you do this, let me just write the final answer. So P1, okay, so here, um, okay, yeah, that doesn't matter. Okay, so it's basically finally what we get is it's the usual random walk probability P of 0n, but then there's an additional factor 1 by n minus 1. And of course, like here you should notice that n can only be even because the return can only happen at even times, right? Because you need to, in one step you can never return, right? So you have to always put, it's 0 for n odd and n even it's finite. So you can, you should verify that if you put n equal to 2, 4 and so on, you can work it out by hand and verify that this is the same. What? Ah, z square, right? Not z, right? Yeah. Okay, so this you should do, I mean, verify. Right, so you should basically just, for first passage, you should just work out all paths that correspond to first passage and work out this return probability and verify that this formula is correct, right? So then for large n, of course, you can see that we recovered the 1 by n to the power 3 by 2 because this is known to be 1 by n to the power half and you get an extra 1 by n. So that's, yeah. Yeah. Two equations for? Yeah, if, I mean, so this is what we found using the generating function approach, and it's a series in Z, and we know that, yeah, you just compare these two series. It has to match, right? No, what do you mean, are they matching? Because for every power, let's say Z square, there will be some Z square term here, right? I just compare those two. What do you mean, are they? Huh? It's clear. After thinking, no. Oh, still thinking. Okay. No, I mean, see, we have two series. I mean, this is an infinite series, this is an infinite series. For every power, there must, that power will be there, right? I mean, I didn't complete it, but you just replace n plus 2 equals to m. Okay, and then it will start from a different, but yeah. Okay, any other questions? Yeah. Which one? Out here? No, see, this we got like doing n plus 2, but this n, no, what is your question? Z2 n plus 1 becomes Z2 n plus 2 divided by, oh, sorry, n plus 2. This is what you are saying. Yeah. Okay, let me check. N plus 1. Okay, did I make a mistake? Huh? Where this 0 is z square and here also z square. So if we put 2, where here? Yeah, I can put 0 to infinity. Yeah, but he's asking like here it should be n minus 1. Why is it n plus 2? I mean, so Zn should have a factor, but I think, okay, you have to work out things a bit carefully. Okay, let me just check my notes. N factorial n plus 1. Okay, so let's do n equal to 2. So what is the first term, right? N equal to 0. Half z square, which is correct, right? Yeah, so I mean, okay, this year you have to just work it out with carefully, but let's just look at the first term in the series. Okay, n equal to 0. So then at 0, this is all 1. So it's z squared divided by 2, right? So z squared divided by 2, first term. Okay, so, huh? Yeah, no, but this is correct, we know, right? Because P12, this we had worked out yesterday, P12 was half, right? So, and this is just a question of just rewriting it. Huh? Yeah, this is correct. Okay. I mean, you might get some factor from here and all that. So you have to just work it out a bit carefully. Okay. Okay, so now I think we are pretty much done with this renewal kind of approach. So now we'll go to this other method, which is the method of absorbing. Okay, and just to be sure, let's look at the n equal to 0 by n equal to 2 term also, right? So if you put 2, I mean, this is 2 factorial. So that's 2 by 1, 1. So Z4, and this is 4 into 2 square. So that's 1/8 Z4. So this should be, so that means P14 is 1/8. Is that correct? Huh? That's what we got, right? So it's correct. Right? So I mean, this is, okay, so now let's do this. Okay, so here the basic idea is, okay, so let's say we are looking at this, so we have, okay, so let's say we ask the question, we start from some origin and we arrive at what is the first arrival probability of first arrival at time n at some point y. Okay, so 1D random walk. So I'm using slightly different notation, and this is space and time. Sorry, this is space, of course. Okay, so okay, I don't want to go this far. Okay, so supposing I'm looking at some point like here. Okay, so I mean here what we the kind of, so if there are 2 to the power n possible walks, and any walk let's say looks like after let's say 6 steps there might be a walk like 1, 2, 3, 4, 5, 6. Then there are some walks which maybe look like 2. So these are 2 possible paths which arrive at y equal to 1, 2, 3, 4 after 6 steps, right? So 1, 2, 3, 4, 5, 6. Okay. So these are 2 possible paths which arrive at y equal to 4 after 6 steps. Out of this, I mean, this one is a first arrival, but this path is not a first arrival, right? Because it has already visited this site once at 4th time step and then come back. Okay. So now for first arrival, we should only count this kind of paths, right? So one way to do that is to eliminate this kind of paths which cross this site y. Okay, and one way to do that is to just put some put a sink at this site, which means every time it arrives this site, after that it can't leave. Okay, so that's why it's called an absorbing boundary condition. Okay, so so then this site we have to say that if a particle comes here, it's not allowed to leave. So then we automatically remove this kind of paths, okay, from our counting. So so basically what we'll say is that let's look at a walk uh, where we put this condition that p at y equal to p at y at all times is equal to 0. Okay, so this is the okay. So why is this condition sufficient to ensure that paths end here? So that we can see if we write the equation of motion. Okay, so the equation is basically for a random walk is p of x at n. Right. Okay. So now, if we are just at let's say at this site, what is the equation, right? Supposing at y minus 1. So at the site y minus 1, the equation will be half p y minus 2n. Right. Okay. So now, what is the probability? So this is origin, and this is the site y. Okay. And if we are here, the probability I'm at this site at time n is so this is y minus 1 and this is y minus 2. So if I can either come from here with probability half, or I could come from here with probability half, right? But now I don't, this side is I don't want anything to come from this side, right? So that means I should set this to 0 at all times, right? So this will basically make sure that this is like a sink. So anything, things can go here, but they can't come back from here, okay? So this will automatically kill all the paths which go like that. And so it will count the right number of paths, okay? Okay, so now how should we find the, finally, of course, we are interested in finding the, it should arrive at this site, okay? So the way to do it is to solve this problem with this boundary condition. Okay, so okay, so now I'll just use some different notation. So we are again solving the same equation, and but I'll call it a solution of this equation with absorbing boundaries. Okay, so basically we want to solve this equation with initial condition. So PA x at n equal to 0 is, let's say, the so let's say initially we always start from the origin, and but we now have a special boundary condition, which is that PA at the site y for all times is equal to 0. Okay, and once we solve this problem, so now basically we, so we have this, we have this line where the probability is strictly 0. Okay, and then the probability is evolving on this half, right? The full distribution according to that equation. So at any time, if we know the probability is here, then we also know that at in the next time step with with probability half, it will go to this site, right? So therefore, the probability of first passage E1. Okay, so this is notation n. Okay, let me just use some new notation. So this is 0 to y. So this first passage at time n from 0 to y is what is the probability that I was at the previous time step. So I've solved this problem, right, with whatever boundaries, and I take that solution and I ask at time, there is the previous time step, what was the probability of being at y. And if I'm at that, then with probability half, I will move to y. Right? So I should put a half here. Y. Okay, that's good. Okay, okay, good. People are alive. Okay, so this is the probability, right? So basically, we have to. So this is the rule. Is clear to everyone? Okay, so now basically we have to first, let's try to recover this result that we had got using this approach, right? So for the 1D walk, so first of all, we have to find a solution to this equation, okay? So in general, this kind of, it's a linear equation, right? And so there are various ways to solve it. So in general, of course, the way to solve linear equations is what? Find the spectrum, like the eigenfunctions, eigenvalues corresponding to these boundary conditions, and then you can solve it. But in this case, there's a simpler way, which is called the method of images. It's very similar to what you do in electrostatics and all. Okay, so the idea is that you can just write the solution immediately just by inspection, and the solution is that P A x n is equal to P Okay, where this Pxn is the solution without any boundary conditions. Okay, so this is the solution we obtained originally, that whatever n factorial by n minus x by 2 factorial and so on. This is without any restrictions. If we solve the problem, then we know this, and then with the absorbing boundary conditions, this is a solution. Okay, so first we can just verify that this is the solution. So first of all, this of course satisfies this equation, right? And this also will satisfy this equation, right? Because I'm just shifting I'm just doing a translation and inversion. So if Px is a solution of the random walk, P of minus x is also a solution, right, of this equation. And then if I shift by some constant, that's also a solution. So both are independent solutions and I'm adding them. So it should also be a solution. Okay, so this is just like solving some electrostatics problem, del square phi equal to some boundary. And if we know one solution, two solutions we can add and they are still solutions. Right? Okay, so so it's a solution, and then we have to check whether the boundary condition is satisfied and the initial condition is satisfied. Okay, so here we can, if we set x equal to y, then you see that this cancels, right? So it satisfies the boundary condition, and then initial condition. So let's say both of them, these solutions are obtained with initial condition x equal to 0. Okay. So then if we put PA. Uh, 0. So then this is of course delta. Okay, so so here it looks like there's a delta. I mean, there's a particle at x equal to 2y, but our interest of the region of interest is between 0 to y, right? So we don't care about this delta function. Okay, so so we have to take this solution only in this part. Okay, so this is similar to electrostatics, right? In the method of images, we find the correct solution in this half, and we don't care what happens in this half. Yeah. Yeah. What do you mean symmetric space around the boundary condition? Okay, so this solution is this solution is very specific to this problem. Like if I had some, for example, if I had a deflecting wall here, then of course it won't work. This is what I'm writing is true only on the if it's on the infinite line. Yeah, there has to be symmetry around y, right? Yeah, minus infinity. Yeah, so it's valid only for this problem where the domain is minus infinity to infinity. Okay. Right. So now once we have this solution, then so this we know already. So this is whatever. So I won't work. Okay. So once we use, then we have to find P1 in 0 to y. We just use this and this. So this is half. So we have to put x equal to y minus 1 and use this, right? So this is P y minus 1. So if you put y minus 1, that's y plus 1. Okay, so again, after this, we already know the forms of this, and after some algebra, you can easily verify that you get back this. Okay, so I won't work through the steps, but it's few steps. Okay, sorry, there's still something. Okay, so this is of course there we were doing 0 to 0. Okay, this is 0 to y. Right, first passage from 0 to y. Okay, so if you work this out, this will give you uh, um, Okay, so this is first passage from 0 to y has this form. Okay, so now if we want to find okay, so here, see, I mean, I didn't, if we want the first passage to the first return time, then it's a bit tricky because we can't put the absorbing at the boundary, right? But what can we do? So if we want the return time problems from 0 to, so 0 to y, we have an exact formula. But if you want 0 to 0, then can we use this result? Huh? See, if it is returning to 0 after n steps, it means that after n minus 1 steps, it has to be either here or this side, right? So it has to be, and it has to be a first passage to this problem without uh, okay, yeah. So basically what I'm saying is, okay, so how do we find first passage from okay 0 to a? So let's say we in the first step with probability half, it will go this way, half this way, right? So after, let's say, first step is this, and then we ask what is the, now from here, given it's here, what is the first return to this line, right? Then that of course automatically gives us the first return to the origin in n steps. Okay, so from here we ask what is the return to this line. So this is 1, let's say. What is the return to the first return in n minus 1 steps? Okay, so basically p of p1 n 0 to 0 is, huh? No, now I'm forgetting the boundary condition problem. I'm just asking, like, without any boundaries, what is the probability of like first return at n steps 0 to 0? Okay, so this I can then frame it as what's the, okay, so in the first step, supposing it goes here, so this happens with probability half. But from here, what is the first return to 0 in n minus 1 steps? Okay, so now this is, so this, therefore this is equal to p, whatever I computed here, p1 n minus 1 0 to 1. Okay, 1 to 0, or which is the same as 0 to 1. Yeah, 0 to 1 and 1 to 0 should be same, right? So it's just, but okay, you can put 1 to 0. Okay, so this we already know from here, right? And so now if you work it out, you will recover that formula. Okay. Okay, any questions?
I have a question.
Sorry? Yeah, so this is probability half, that is also probability half. Then you add the half goes away, right? That's why I didn't put a half here. There are two processes which will lead there. So yeah, I can write half and then plus half of the other one, but those probabilities should be the same, right? Going from here or going from here back to here. Was there a question from someone online? Or?
I had the same question.
Someone is saying something. No. Okay, so Okay, so this method, of course, we did in 1D, but it's very general. I mean, if you have a, let's say now, 2D lattice, right, and you start from some place, let's say the origin, and you go to some, you ask what is the first arrival time at this site. Okay, so again now what we should do is we should only look at paths which don't cross this, right? So so in general you'll solve the equation. So we'll put basically at this site we'll put the probability should vanish, right? So if it vanishes, then things can't go out from here, and then we have to solve this equation. So it's the same equation, 1 by. Okay, so basically we have to solve this boundary value problem. At this site, it's the probability always vanishes. This is the initial condition, and this is the equation, right? Okay, so supposing somehow we are able to solve here, clearly the method of mirror may not work so well because it's a more complicated geometry, but somehow we will be able to, supposing we can solve it. Then how do we find the first passage time? So what will we do here? So now what is P1 first time from 0 to y? So given this solution of this equation, how will we find this? Huh? Right, exactly. So at nth step, if it has to be here, at the previous step, it has to be in either of the neighbors, right? So basically, we have to sum over all the neighbors of site Y. So I'll just call it. I mean, okay, so PA. Okay, so it doesn't matter. Okay, so this means sum over all x's which are neighbors of y. And from each neighbor, the probability of hopping is this, right? So this is the formula. Okay, so okay, so maybe let's also see like how this method is kind of slightly more powerful than than the previous method. Like we have two different methods, but each you can use them in different ways in different like huh? Sorry, say again? Yeah. No, there is a point, right? So, I mean, so in this 2D lattice, I mean, if you look at paths, okay, so let's say, okay, so you start from this and then you are interested in first passage, let's say to this point, right? So you can draw a trajectory which looks like, let's say, uh, this. So after you ask for after 6 steps, what is the probability I'm here, right? So one trajectory is of course 1, 2, 3, 4, okay, 5, 6, okay. And so this is a trajectory which crosses this point, right? And then you can have a trajectory which is maybe goes like that. Okay, so this trajectory of course didn't cross, right? So, I mean, you just rule out this kind of trajectories which cross. I mean, you can't draw lines now because it's just a point, right? I mean, if you want to draw, you have to draw in like 3D because that was time, right? And this is space. Then, of course, this will be a line. If you draw in space-time, then it's a line which is never crossed. Okay, so uh, okay, so maybe I can just make some remarks about the this. There's some relation to currents and so on, which is easiest to state in if we are working in the continuum. Okay, so here what I'm writing, it is actually it's the in some sense it's the current that's flowing into this site. Okay, so supposing we are doing this problem like for the diffusion equation, okay, or Brownian motion. Okay, so then you can do the same thing, and let's say there what would we do? So there, I mean, what we have to do is solve the diffusion equation. So I'll call it V of X. Okay, so we have to solve this equation with, let's say, boundary conditions that P vanishes at some point. Right? So let's say P at Y at all times is equal to 0. Okay, and then if we ask like what is the first passage at time t, then it's basically we can ask given this equation. So okay, so here so from this equation we know there's a current, right, which gives the number of particles per unit time. So what is the current at y? What is the current? Huh? No, the current is not 0. P is 0, but the current is not 0. There's things flowing, right? Yeah, it's okay. So if there was a diffusion constant, it's basically minus d del xp, right? So this is the current. Okay, and if you evaluate the current at this point y, so then it tells you per unit time how much particles are going in, right? So this is precisely the therefore the probability that a particle is absorbed for the first time at time t. Okay, so in fact uh, I mean, this is just the continuum version of what I wrote here. Okay, so it's just the current evaluated at. Okay, so maybe let's quickly work this out. Okay, so now what is the solution of this equation? Okay, so let me again put this A here. So given this yeah, and the initial condition that P A at x equal to 0 is equal to delta x 0. So what is the solution of this equation? Huh? So you're saying it's this? Yeah. Right, yeah, exactly. So we have to do the same thing, right? To subtract whatever. So we have to subtract minus e to the power. So basically we have to, the solution is P xt minus this is the solution. So we have to do minus t. Okay, so this satisfies this set of equations, and now we have to find the current. So we take derivative with respect to this, and then set x equal to y. Right. So if we put derivative, then what do you get? So the first is uh, okay. Is this right? 2y minus. Is this right? Huh? Okay, no, so there was a d here. But the sign looks wrong. Oh, okay, so maybe minus. Okay, so now we put y equal to x here. Correct, right? Okay, now we put x equal to y, so then minus c is equal to, so if you put y, so then they become the same, so it's y by t. Okay, so we get back exactly what we had written here, right? In the, so this was the discrete answer, but now we got back, even for the diffusion equation, we got back exactly this. But here, I just wanted to tell you that basically what we are computing is the current that's flowing. Okay, so what else? Okay, so maybe I just mention a few more things which yeah, which kind of explain this uh, like this kind of problems in a more general setting. Okay, so one question is like, okay, so so this is again part of the assignment problem. Like if I did this on a finite lattice, so this you should try. But so let's say you have a finite lattice like this, and if you have, let's say, hopping rates like p and q. So then how do, or let's say, okay, let's start with half half. Okay, now how do you solve this problem of this with this absorbing boundary conditions? Okay, so so this method of images will clearly not work, right? Because like someone said, you need this infinite domain to use this method of images. So okay, so you can do something you can do. Okay, so the method of images, basically the idea is, okay, so see what you're doing is, let's say you have you want to find the probability of going to some point X by for paths which don't cross this. Okay, so then for paths which cross this line, so they look like, let's say, okay, so there are two kinds of paths. Some paths cross this line and come here. Some paths don't cross. So we want to remove all such this kind of paths. And what we do in the method of images is like we solve a problem where this point has we look at the image of this point, which means it will be some point which is placed at what distance. So it should be this distance, which is y minus x, plus this distance, right? So that's y. So that's 2y minus x. Okay, so supposing you ask for all paths which go to this point. Okay, now, so what you can see is that for every path like this, there will be a path, there will be an image path which looks like this, which ends up at this point. Okay, so for all the wrong paths that landed up here, there will always be a path which goes here. Okay, and for all paths which reach here, they are all correspond to wrong paths leading to this point. Okay, so that's what we basically subtracted all the paths which went to this point, right? That's what we did. Okay, so okay, so this is actually again nicely described in this Chandrasekhar's review article. Okay, but and if you have okay, so now you can ask, like, if you have some reflecting wall out here. Okay, so this problem, if it's on a finite ring, you have to put some boundary conditions, like what happens at after when you reach the this site, right? So so let's say we have hopping half. This way you can go half. Out here you can go half. Now if you do half like that, then there's a problem, right? Because this probability of going out is half, but it should be probability 1. From every side, probably things going out should be 1. So what can I do to fix this? I can, yeah, there are many things one can do. One is to introduce a probability of staying here, which is half. Okay, so so this is, I mean, so now if you ask, like, what does this correspond to? If you write the equation of motion, so there you have some term, let's say half of p. So if you're writing the evolution at point L, so this is site L, the last site at N. So this will be half L minus 1, N minus 1, plus P, L plus 1, N minus 1. Right, yeah. So this boundary condition corresponds to, like, if I, so there's no such point, right, L plus 1. But if I want to put this kind of a boundary condition, that's equivalent to saying that this is equal to, so I can just say that this is equal to PL n minus 1. Okay, so this is like, It's reflecting boundary condition, because if you think about it, if you kind of think of the continuum limit, this corresponds to what? Gradient of P equal to 0, okay, which is like no current flowing. Okay, so there are two boundary conditions. One is absorbing, which is, let's say, at some point y equal to 0. This we discussed. But reflecting boundary conditions means this is 0. This is absorbing. Okay, and this is the lattice version. Okay, so you can have continuum versions which are like easy to understand physically. This is current going to 0 and this is probability. And here it's the lattice version, right? L plus 1 is equal to L. So if you want to solve this problem and like compute various things, so basically you have to solve, so again you have to solve this equation, PA with the boundary condition that and then supposing what we are interested in is like the first passage from some point x to 0. Okay, so we want we shouldn't say 0 to x. Then this boundary becomes irrelevant, right? If we say a first passage from 0 to x, okay, so instead we let's say x to 0. Okay, so this I think this is part of the assignment. Find P1 first passage from some point x to 0 in this finite lattice. So finite lattice just means that there's a reflecting wall here. And now if you want x to 0 first passage, you have to put an absorbing boundary condition here, right, at 0. So you have to basically solve this problem with also PA at 0 n equals to 0. So this is, so there's a reflecting wall here, there's an absorbing wall here. And of course, initial condition now is PA is equal to, okay, so this is now a bad notation because, okay, so instead of x, maybe I should say maybe x naught. Okay, so this is n delta. Okay, so x naught is some point on this line. Okay, so it's a finite box, and we, if it goes here, it gets reflected, and we want to know the first passage from here to here. Okay, so now we have to solve this problem. So this you should try to think. So like I said, so you can try to do this method of images, but that gets very tricky. The other way to do this kind of problems is just to find the appropriate eigenstates. Okay, so I mean, in general, like so we discussed this, if you have some equation like p, so this is our general formalism, right? For any Markov process you can write it like this. And then we said in the in the preparatory schools that if we know the eigenstates phi in then we can write the propagator and so on, right? So that's a more straightforward method of solving this kind of problems. And okay, so maybe first you can try solving this problem using this method, and then you can try to solve this problem. So this is, I leave it for the tutorials. But people should try, and if you don't, then we can work out the solution. Okay, it's a very good problem to do. Okay, maybe the last remark that I'll just make in 2 minutes is because someone asked about Markov versus non-Markov processes and so on, right? So far I have everything I'm discussing mostly in the context of random walks, but for any Markov process where you can write this kind of equation, it's valid, right? So I mean, one example which maybe is interesting because there are a lot of people here from active matter is like there's a model of non-Markovian random walk, which is called so this is one of the simplest example of a active random walk, let's say. It's called the persistent random walk. Okay. Okay, so this is a walk where every time it takes a step, the next step, if it's at x n, then xn plus 1 depends on both xn and xn minus 1. Okay, so so the persistent random walker, basically persistence means it tries to do the whatever it was doing, it tries to do the same, continue to do the same thing. Okay, so if it was moving in, let's say the previous step from n minus 1 to n, if it was in the plus direction, then with more probability it wants to continue like that. Okay, and with less probability it wants to change direction. Okay, so basically xn plus 1 would be xn plus with probability q with probability p, and it's minus xn minus 1 with probability q equals to 1 minus c. Okay, so this is a walk which has some memory, but you can easily make it a Markov process by just defining a new variable. Okay, so this is always like if it's a finite step non-Markov process, you can always convert it into a Markov process. Okay, so basically if you define a kind of a velocity variable, which is let's say Vn, so let's say Vn. Okay, so Vn can only take values plus 1 and minus 1. Okay, then you see that we can write an equation for xn and Vn together. Okay, and then it's a Markov process. Okay, so basically xn plus 1 is xn plus Vn, and Vn plus 1 is equal to either, sorry, xn plus 1 minus xn. Okay, so this is so if you define, so it's basically the particle carries a kind of a spin variable, which can be plus 1 or minus 1. If it is plus 1, it will do something. If it is minus 1, it will do something. Okay. So that's the dynamics. Okay. So this I think many of you have seen. So my main point is that you can convert this also again back to a Markov process. And then you can again apply all this formalism. Okay, so in particular, you can ask the question like, if I have a persistent random walker at position x and the internal this velocity variable v, after like what is the first return? So it both this keep changing with time. So what is the first time I get back this value? So you can ask this. So a lot of questions in active matter can be again brought to a Markov process, and then you can use the same formula. Yeah, okay, but it's not a biased random walk. Okay, so there's no bias, even though it looks like there's a bias, but there's no bias, right? So actually, if you look at the long-time asymptotics for the persistent random walkers, it's not like the biased random. So biased random walker would be exponential minus t, the return time, but this one will still be 1 by t to the power 3 by 2 at large times. Okay, so it will still be like the random walk. Because yeah, at long times it basically looks like a random walk. Okay, so this is everything about classical first passage problems. So from the next class, we'll start doing the quantum problem. What is really, I mean, very interesting is that like many of these formalisms kind of, again, can be applied in the quantum case, even though there, like the quantum case, of course, is much more subtle because just the definition of the process becomes very difficult. Okay, so we'll first discuss how exactly to define the problem, but you can start thinking about it. Like the basic idea is like you have particle described by wave function, and you start from some initial state and let it evolve, and you have some, let's say, a measuring device, right? Some screen or something, and you are waiting for the particle to get detected, and you ask when is the time that this particle gets detected. Okay, so you can start maybe just thinking about this problem, and we'll start discussing tomorrow.